Hello everyone, and welcome back to the CS184 discussion recordings. Today we're going to go over half edges and ray surface intersection. So let's talk about some meshes. So the first part of this discussion is just the half edge data structure. And so the half edge data structure is a pretty powerful, pretty useful representation for polygon meshes. And so the key part of this is the half edge, which is why it's named the half edge data structure. So this drawing right here kind of gives a good example of what this data structure is all about. And so the key of this is the half edge that's labeled right here on the diagram. And then the other parts are, so there's next, face, edge, and twin. And so this is basically the entire data structure. And the key is the half edges. So the half edge has an edge, which is the edge it's associated with. It has a twin, which is another half edge on the other side, which is associated with the same edge. It has a next, which is the next half edge, which is, on this in the same triangle as this half edge. And then it has a face, which is the triangle that this half edge is associated with. So basically, if you look at this table, the half edge has pointers to all these things: the twin, next, vertex, edge, face, where twin, next are both half edges. And then there's also elements vertex, edge, and face, but all they know is their corresponding half edge. So the half edge is the key to the whole data structure. That's the most important part in manipulating the mesh, editing the mesh, anything. You work around the half edge. So the half edge is essentially the glue that holds the whole thing together. So let's do some practice on using these relationships, twin, next, edge, face, all that, to actually manipulate meshes, work with meshes. So let's go through some problems. So first up, problem 1, starting from a given vertex, traverse the mesh and return a vector containing all of the edges that are opposite that vertex. In the diagram below, the opposite edges are labeled. Hint, start with the vertex's half edge and then perform a do while loop until we return to the original half edge. Okay, so looking at this diagram right here, we have vertex V in the middle. So that's, the vertex. And then the edges, the opposite edges, are all labeled, so E1 through E6 around. Okay, so now the first thing, one thing we learned up here is that a vertex has only a pointer to a half edge, one half edge, right? But looking at this diagram, you'll notice that there's many half edges in the diagram, right? So which one is the one? And you don't know. But the way it works is the half edge for a vertex is a half edge, could be any half edge, that points away from it. So it's going to be maybe that one, or maybe that one, or maybe that one. These are all valid half edges. Okay, it could be any one of those. But what we're going to do is write this method in a way that it doesn't quite matter which one it is. It's going to work anyway. Okay, so let me get rid of that. Okay, so what we want to do now is start with the half edge, and then we want to get all the way to this edge on the other side, right? So how do we do that? Well, let's just assume that that's the half edge we get right there, right? Okay, well, so from this half edge, we could get a number of things. We could get the face. That doesn't really help us. We could get the vertex. Well, we already know that. We could get the twin. That also doesn't really help us. And here, I'll draw the twin in blue just so you guys can see what it looks like. There you go. And we could also get next, and I'll draw that in red. So there's next. And so if we think about this, of all these things we have, next would be useful because next is actually connected to the opposite edge, E1, that we're interested in. So the way we could get E1 is by doing something like, let's say this half edge is called H. H, right? Then what we could do is we could say H dash next. So that's going to be that red vector. And then we're going to call edge. And that's going to give us E1. Sorry, this is really messy. Let me write that here. H next edge, right? And that's E1. Okay, there we go. So that's what we want. Well, it's okay. So we got E1, we can add it to a vector. And then the next step is we want to be able to move on, right? We got E1, now let's get E2. So how would we do that? Well, in this case, we drew next in red and twin in blue. I think twin would be useful here. So what we could do is we could say, well, let's get its twin, that's the blue one, and then let's get the blue ones next. And what does that look like? We can draw that in red. Looks like that, right? And so if we then wanted to get the next half edge, the new h, right, we can make this h prime. We can do h prime is equal to h's twin next. Okay, and then once we do that, we can just do exactly what we did up here for E1, but for E2, and then do this again, E3, E4, E5, E6. Okay, so these are kind of the fundamental building blocks to this, function that will allow us to get what we want. Okay, so because of the way I have this set up, I'm not going to actually go through and write this code all out, but instead what I'm going to do is I'm just going to come over here and I'm just going to show you the solution and then we'll walk through it. So we go through line by line and we'll look at where these building blocks that we looked at just now fall into play. Okay, so let's see the solution line by line. First, just creating a vector of edges to store it, nothing crazy. And then we say half edge h is equal to v dash half edge, okay? So remember, now we don't know which half edge we're getting, but we get one half edge. We store it. Now here's the key. We save start h is equal to h, okay? So we're duplicating this and remembering which half edge we started at. All right, and then we do a do while loop. So do while edge dot pushback h dash next dash edge. Now if you come back here, that's exactly what we did right there to get E1, right? So what we've done is edges dot pushback E1, okay? And then we look at this. So, okay, so in this case, they actually went the opposite way. So what we did was, we said, how do we get to E2? And we did that with twin dash next, and then we could do it again. But you could also, if we get rid of this and get rid of that, what we could do is we could say, okay, well, we have next, we have this red one. What if we got next again? That's that one. And then what if we got the twin? That's that one, right? And so that can be our h prime. And once again, we do the same thing. So that's another alternative is h prime is equal to next twin. Okay, so one of the keys here is that there's two different ways to do this. Basically, we could move around this mesh in multiple ways. There's not just one solution. And that's kind of one of the good things about the half-edge data structure is there's multiple ways to accomplish the same thing. Okay, so coming back to the solution, so now we go h dash next and next. So let's say we started here, we added E1, now we're here, right? And okay, so then while loop, so we check, are we back to where we started? Nope. Okay, so then we're going to add E6 and then move here, add E5, move here, add E4, move here, add E3, move here, add E2, and then we're going to come back here, and when that happens, this while loop is going to trigger. We're back at start H, and so we're just going to go ahead and return edges. Okay, so that's the whole method, nothing too complicated. The key parts are right here. So this H dash next dash edge and then H next twin. Okay, those are the keys. That's what you want to keep in mind for this method. That's the key part. Okay, so let's keep going. Let's look at another problem using the half-edge data structure. So let's write a function that locally attenuates noise in a mesh through a diffusion process. To do so, we will approximate the Laplacian operator using the umbrella operator at a specific vertex. So this is kind of a lot of fancy words. Don't worry about any of that. then we'll apply the approximated Laplacian to a given vertex to locally smooth the mesh around that vertex. This void function should directly modify the vertex V's position, okay? So more specifically, okay, so this equation basically is the math of what we're doing. What we're doing is we're going to all the neighboring vertices, subtracting the difference, subtracting the position, so find the difference, average that, that's the 1 over n, and then we're using this rule down here to find a new position, basically. Okay, we're just slightly moving it towards the average of the positions to smooth the mesh out in total. Okay, so let's think about this. Let's think about how we want to do this. Just like last time, right? Just like last time, we want to be able to get away. So if I erase this, let me just erase all of this actually. Okay, so now we're here. We have H, and what we're interested in is that right there. We want to get the position of that vertex right there, right? But keep in mind that a half edge only has reference to one vertex, and that's the vertex it originates from. So for this H, the vertex, its corresponding vertex is the center one. So for this, the vertex we're interested in, this one in the corner, we want that green half edge, right? And so the way we do that, I mean, hopefully you guys recognize this from what we were doing in the last problem. It's H dash next, right? So we're going to use H dash next to get the half edge and then get its vertex and its position. And that's how we'll complete the Laplacian operator. Okay, whoops. So let's go over here and let's take a look at how this one is done. Okay, so once again, not a huge method, pretty simple. So we start off with L just 0, 0, 0. Basically, we're just initializing it to nothing. Same as before, get H, the half edge, get the start one so we know when we've looped back around. This time we're going to keep this variable n, right, to count how many neighbors we have, because when we come back, we want to be able to average by that n, divide by that n. And then, so the do while loop again, right? And once again, the stopping condition is when our H is back to our starting. Okay, so the first line right here, vertex iter, v underscore j is equal to H next vertex, right? That's what we just talked about. So we're going to take H, we're going to come up here, take this H, take that next, and then take the vertex. And that's Vj, right? Okay. Now once we have Vj, we're going to get its position using the position method, subtract the two positions, right? This is just following this math equation up here. Subtract the two positions, add that to L. So we're just keeping a running total in L, just once again following the math equation. Increment n, because now we've visited one more neighbor, and then do exactly what we did last time. So H dash twin dash next, okay? So remember last time, if we come up here, we used H next next twin. But we discussed earlier how there are kind of multiple ways to move around the mesh. And so for part 2, we're actually using the opposite one. So here, last time we went left around the mesh. This time we're going to go right. So we're going to go H, get its twin, and then get its next. And that's how we're going to get H prime, okay? So once again, multiple ways to do the same thing with these half-edge data structure. So problem 1 goes left, problem 2 goes right. They both work. There's nothing wrong with either one. Okay, and so we move H over and just keep doing this loop until we get back to the beginning. And once we're back to the beginning, basically, we've gone ahead, we've accumulated L, we've been, adding this Laplacian. So then what we do is we basically just implement this last equation, right? The position is equal to the initial position plus k times L over n, and we divide by n because it's right here in this equation, and that's it. We've implemented the Laplacian local smoothing operator. Okay, nothing too complicated. Once again, the key part of this is how do we move around the mesh. So in this case, H next vertex to get the vertices that are neighboring this vertex, and then twin next to keep moving. Okay, so that's that's the key for these problems. You guys will see a lot more of this half-edge data structure on project 2, specifically with the edge flip, split, and then upsampling. You'll become way more familiar than you want to be with this data structure. Okay, so let's keep going. So that was the half-edge data structure. Now let's look at this. So the figure below shows some local structure. So just kind of a piece of a mesh, and it's really labeled. You see all these edges, faces, vertices, all that. So to contract the edge connecting vertices V0 and V2, we need to first update some fields of those elements shown in the figure, then delete V2, delete half edges E1, E2, E4, E5, E7, E8, and faces F0 and F1. Fill in the blanks for how the following fields should be updated in order to minimize changes in the whole operation. Okay, so this is very similar to something you'll see on the project, right? With edge flip, with edge split, you'll be doing operations very similar to this. And so what we want to do in this case is we have V0 and V2, and we essentially want to just combine those into one and delete this entire middle section. Okay, so what I highly, highly recommend you do for all problems of this type here on tests, on project, anytime you see something like this, is draw a diagram. Draw a diagram, label it well, and it will make everything way easier from then on out. Okay, so I've gone ahead and drawn a diagram for this problem. So here we go. Okay, so this is the before, the one up here is before, and then this is after. So as you can see, basically those middle two triangles, F0 and F1, just disappear. We got rid of them, and all we have is F2, 3, 4, and 5, and just V0 in the middle, okay? And I've gone ahead, labeled the same edges. We deleted some, so this is what's left. And now that we have this, basically, answering this question is actually very easy, because all we have to do is look at the diagram and just read off the answers. Okay, so if we come up here, let me do it like this. Okay, so E11 dash next. Okay, so what is it? We have this triangle, there's E11. We just read it, and it's E0, right? Whoops, E0. Nice and easy. We just look at the triangle E11 is and look at the next one. Okay, F3 dash half edge. So where's F3? It's in the bottom left here. And so for a face now, a face has multiple possible half edges. Just like a vertex, any edge that's part of this face could be the half edge. And so this is going to have multiple options, which is going to be E10, E0, and E11. All valid answers, okay? Any one of those is correct. And then, so let's keep going. Now we're going to look at V0's half edge, okay? So V0 is right here in the center. And so we just want to look and see what half edges are going out from V0, going away from V0. And any of those can be the answer. So let's see. We have E16 going up and to the left. We have E0 going straight to the left. We have E9 going to the right. And then E12 going down and to the right. Okay, so those are all valid half edges. Any of those is a correct answer. Okay, let's keep going. Now, E3, the face of E3. So we just look here and find E3 right down here in the bottom right and just look at what face it's part of. F4. Easy. So F4. Okay, and then E12's vertex. So we find E12. It's right here in the bottom right, kind of going out. And we look and say, where does it originate from? So it originates from the center, V0. And so that's its vertex. There you go, V0. Okay, so once we drew this diagram, this problem became much, much easier. Rather than having to visualize everything in our head, we can just look at the diagram and read the answers right off. But, F3, the faces half edge could have multiple options, and same with the vertices half edge. So that's always something to keep in mind. It could have multiple options. Any one of them is correct. Okay, so the key here is draw the diagram. Always draw the diagram on the project, homework, tests, anywhere. Draw the diagram. Okay, let's keep going. So now that's all for half edges for this discussion. You'll become a lot more familiar with those during the project. Let's talk about ray surface intersection, because this is kind of the first topic in the area of ray tracing. So given a mesh representation of an object, we want to render it. To do so, we need to know which parts of the object are visible, where to put shadows, where to put the lighting, all of that. So the one thing we could do is take a ray and intersect it with every triangle, because meshes are made up of a lot of triangles, right? So we could intersect it with every single one, and based on the intersections, we'll know what we're seeing, what the lighting looks like, all of that. Okay, so rays in this class and in general are defined with two parameters, O and D. So O is the origin, basically where the ray starts, and then D is what direction does this ray move in. Okay, and then the position of the ray, R at T, can be written according to this equation. R of T is equal to O plus TD. So basically O is the starting spot, and then for every time step T, you move D. Okay, so after one time step, you'll have moved D. After two, you'll have moved 2D, so on and so forth. Okay, so as a warm-up, let's rederive the equation for a ray intersection with an arbitrary plane. Okay, so the equation for a plane is given right here. It's P minus P prime dot N is equal to 0. So N is the normal, P is just any point on the plane, and then P prime is another point on the plane. Okay, so this basically tells us all points P which satisfy this are on the plane. Okay, so let's solve for this ray intersection by essentially setting this point P, which should be on the plane, equal to R of T, which tells us the position of the ray at a certain time, and then solving for T. Okay, so let's go ahead and do this. So we have P minus P prime, so I'm just going to put R of T minus P prime dot N is equal to 0. Okay, so let's go ahead and split this up. So O plus TD minus P prime dot N is equal to 0. Move down. Okay. Now what we can do is we can do a little bit of distribution. So we can go, because we want to isolate the T, right? We're solving for T. So we can do O minus P prime, all of that dot N, plus TD dot N is equal to 0. Then we can do TD dot N is equal to O minus P prime dot N. And then let me come up here, and then we just divide. So T is going to be equal to O minus P prime dot N all over D dot N. Okay, and there we go. That's our answer. So basically, given an array which has parameters O and D, and given a point on a plane P prime and the normal N, we can solve for the time T at which this ray intersects the plane. Okay, and so given T, we can then also find the point easily by plugging it back into the ray equation, right? Because now that we have T, we can just plug it into O plus TD, and then we know the exact position also. Okay, so this is a useful equation. We'll use it for ray plane intersection. So let's keep going. So now let's look at what this T means. So T is the time when we intersect. So what does it mean if we get a value of T is equal to T less than 0? Okay, so I find it useful in a sense to kind of think about this as, let's say we have this point here. This is O, right? And then let's say we go this way, this much, that's O plus D. Then we can go a little more, and that's O plus 2D. We could go a little more, and that's O plus 3D, right? Every time step we move by D more. So what if T was less than 0, right? Then it would be O minus D, or O minus 2D, or O minus 3D. And where would that be? That would be here, right? This is O minus D, or you could go further, O minus 2D. So what does that mean? That means that getting a value of t less than 0 means that this intersection is happening behind the ray's origin. Essentially, the ray is moving in the opposite direction, and this intersection is behind it. So that means if you get value t less than 0, it's not valid. So t less than 0, not valid intersection. Essentially, if time went backwards and the ray went backwards, maybe, but it's not, that doesn't happen. The ray moves forwards in the direction, so it's never going to intersect this. And so that's what that means when we get a value of t is less than 0. Okay? And keep in mind that this can happen for anything. So in this case, we're talking about planes, but anything. It could be with a sphere, a triangle, any shape. If the t is less than 0, it's not a valid intersection because it means it's behind the ray. Okay? So let's keep going. So the next question is, what does it mean if d dot n is equal to 0? So d is the direction of the ray, and n is the normal of the plane. And if you watch the linear algebra intro discussion, you know that if the dot product of two vectors is 0, that means that they are perpendicular. So there's 90-degree angle between them. And so if the direction of the ray, whoa, what's going on? The direction of the ray and the normal are perpendicular, well, the normal is already perpendicular to any vector on the plane, right? That's the definition of a normal. And if it's also perpendicular to the direction of the ray, that means either the ray is on the plane, right, which would make it perpendicular to the normal, or it's parallel to the plane, right? Those are the only two options. It's either on the plane, or parallel to the plane, right? And so given this, we can kind of make some assumptions or make some inferences about the intersections, right? If it's on the plane, that means there's infinite intersections. And if it's parallel to the plane, there's 0 intersections. Okay? So if the ray's direction vector is perpendicular to the normal vector, it either has 0 intersections or intersects everywhere for all values of t. Okay? So another useful fact to keep in mind, this doesn't end up happening nearly as much for other shapes. So, for circles, things like that, you won't have it, but it will happen for triangles, and it's a good idea to keep it in mind for planes also. Okay, so let's keep going. So the next question is, given the following implicit representation of an ellipsoid and the following ray, compute the positions at which the ray intersects the ellipsoid. So f of x comma y comma z is equal to x squared over 4 plus y squared plus z squared over 4 minus 9. So that's the equation of an ellipse, or 3D ellipse. And then we have the equation of a ray. So r is equal to 0, 1, 0 plus t times 1, 0, 2. So now remember, based on the structure of the ray equation we set earlier, we can write, we had r is equal to O plus TD. So O is equal to 0, 1, 0, and D is equal to 1, 0, 2, right? Just reading off the equation given to us. Okay, so now we want to find when this intersects. So we want to find when this position, when r of t satisfies this equation here, f of x y z is equal to this. So start by substituting the ray r of t into the function to get an expression f of O plus TD, set that equal to 0, and then solve for t. And then we can plug that back in, okay? So let's go ahead and do this. But first, let's split the ray into its components. So the x component of the ray is equal to 0 plus t times 1, right? So just the 0 from here plus t times 1 there. Y is equal to 1 plus 0 times t. And then z is equal to 0 plus t times 2. So that's equal to t equal to 1 equal to 2t. Okay, so now we have individual expressions for x, y, and z, and we can easily plug those back into that equation for the ellipse, right? And set that equal to 0. So let's do that. So 0 is equal to x, which is 1, is equal to t, equal to t. So that's going to be t squared over 4 plus y squared. Well, y is just 1, so that's just 1, plus z squared over 4. Well, z is 4t, or so 2t, so it's 4t squared over 4 minus 9, right? So this is the equation we have. So what we can do, we can keep simplifying. So 0 is equal to, add these up, so that's 5t squared over 4 minus 8, right? Keep solving, so move the 8 to the other side, and then we'll get t squared is equal to 32 over 5, right? And then if we take the square root of both sides, we'll get t is equal to plus or minus 4 root 2/5. Okay, so we took the ray equation, split it up into its x, y, and z components, plugged each of those into the ellipse equation, and then now we got this t. So we have a plus and a minus t. Now remember, earlier we talked about what a minus t means. It means it's behind the origin of the ray. So that's not a valid intersection. So we can just, in this case, throw the negative t completely out. And the only t we care about is positive 4 times the square root of 2/5, right? Okay, so now that we have the t, we want to find the actual point of intersection. And how do we do this? Well, we just plug it back into the ray equation, right? We find the position of the ray at this t, and that'll be the intersection. So let's go ahead and do that. So what that's going to be is, here, let me kind of separate this out. So 0, 1, 0 plus 4 root 2/5 times 1, 0, 2. Okay, and so we're basically just going to scale this d by 4 root 2/5 and then add. So there we go. So this is just going to be 4 2/5, right? Because this one's 0, so it's just going to be 1 plus 0, 1. And then this is going to be 0 plus 2 times this, so 8 root 2 over 5. And there we go. That is the point of intersection between this ray and this ellipsoid. Okay, so nothing too crazy. We took the ray, split it into its xyz, plugged it into the ellipse, found the intersection time, threw away the negative intersection because it doesn't mean anything, and then plugged the time back into our ray equation, and we got a nice answer. Okay, and so that's it. That's all for discussion this week. This Thursday, we'll be going through some more ray intersection, talking about intersecting them with triangles, which is really important for actually rendering meshes. So that should be interesting. See you then.